Good afternoon, everyone. It is officially 1 o'clock. I am Amy Susan with Missouri Enterprise, the Show Me State's manufacturing expert and dedicated MEP center. I'd like to welcome you to our webinar. It's our last one for the month of July in our July webinar series, utilizing 3D printing to save manufacturers both time and money. Before I kick it over to our tech expert, Bob Beckman, hello, who's joining us from St. Louis, thanks to our lovely virtual Zoom platform. But before I give it to him, I just wanted to give you a little bit of information about Missouri Enterprise and just kind of what next steps are for us. So we are funded by NIST. NIST is a division within the U.S. Department of Commerce, and this funding enables us to serve companies like yours in a variety of ways, whether it's helping you obtain industry certifications, accessing and implementing technology like the one we'll be talking about today, workforce development, continuous improvement projects, workplace safety, growth plans, how to transition through COVID, all those things and more. And in order to maintain this federal funding and to continue to serve you, we are asked to provide input to our federal partners. So towards the end of this webinar, I'll be launching a brief poll. It's 5 questions, and it just allows us to gauge how successful we were, if the webinar was helpful to you. So you'll just click on your button on the bottom once I launch that, and just, again, it'll take you 10 seconds to answer those questions. Within the next few days, we'll also send you a link to just a very basic NIST survey. It's via SurveyMonkey, and again, it just asks you a few additional questions. That's really all I wanted to cover today. So really want to appreciate Bob putting this presentation together. This, of course, is a growing technology, and it's not just for the big guys. It's not just for the big manufacturers out there. These are small manufacturers, even in the Show Me State, that are utilizing them. And Bob, I know you have a lot of experience here. There's also resources throughout Missouri. If you don't have a 3D printer, Bob, I know you're probably going to share some of those resources or links or direct them on where to go, where they can access some of these tools at their disposal. So with that, thank you, Bob. Take it away.
Well, thank you, Amy. Good afternoon, everybody. We're going to be talking today about 3D printing. And 3D printing has really gotten big of late, but it's been around for quite a while. But before we get started, one of the things I want to talk about is what's in a name. There have been a lot of different names associated with 3D printing. When I first started in seeing this process, it was probably in the mid 80s. So we're talking 30, 35 years ago that I really started seeing, at the time we called it rapid prototyping. So I saw that when I worked for McDonnell Douglas, now Boeing. We used a lot of rapid prototype parts. Since then, it's kind of been called a lot of different things. Most people call it 3D printing. We kind of have changed the naming. Everybody's now calling it, at higher levels, we're calling it additive manufacturing. So that is actually the proper term. I will use all 3 interchangeably during this presentation. But additive manufacturing is kind of the proper name for it. And the difference is most manufacturing is subtractive manufacturing, where you would take you're removing chips, you're taking chips, whether it's a lathe, whether it's a drill press, you're taking parts away, whereas additive manufacturing, you're actually adding things to create the part. This presentation will be kind of a additive manufacturing 101. So you will get a lot of, hopefully at the end of this, you'll have an understanding of what we're talking about and the different types of additive manufacturing 3D printings around. So this was the first major exposure. 2013, someone came up with the idea of what if I 3D printed or produced a gun? It hit the news everywhere. It was on the media, all the different channels. And everybody was worried about this new technology and what that meant for the future. But really all it was is just something else being created with additive manufacturing, with 3D printing. It's really not a good application for 3D printing for reasons I'll talk about during the presentation, but it is something that it just shows another example of what can be made with that. So when we talk about 3D printing, what are some of the reasons why you would or would not use this kind of technology? Start off with the cons. It is a little bit more, it is significantly more expensive than like an injection molded part. If you're going to compare it to something that you're going to run off, you're going to make a widget out of plastic. It's going to be significantly more expensive, and it's going to take a lot longer to make that part. But there's reasons why this is actually, why 3D printing is an advantage. Sometimes there are some work you need to do after you make the part, whereas when it comes off of a injection molded part, it comes out of injection molded machine, it's done, it's ready to go. But sometimes with 3D printing, you need to do some post-processing. Large parts are hard to do with 3D printing. It's becoming a little easier, but it is hard to do. And also the materials and the mechanical properties of those materials sometimes aren't nearly as robust as what you would find in injection molded or other manufacturing processes. But we talked about the pros of 3D printing. This is where it really shines, is you can get very complex. You can have the whole thing come out of the machine and it's done. It's already assembled. Multiple parts can be built as one. There is very little waste when you're doing 3D printed or additive manufacturing parts, whereas in injection molding or subtractive manufacturing, you're going to have the sprues or the lead-ins of the plastic that's waste. It has to be reground, or you've got the chips on the ground. So there's very little waste. Everything that you're creating actually goes into the part you're making. You can do things with the colors, where with injection molding, you're shooting one color of plastic, whereas with 3D printing, additive manufacturing, you can do a rainbow built into it. There's a lot of other options. But let's talk a little bit about the different types of additive manufacturing. We kind of break it into 7 different food groups here. I'm going to go through each one, explaining a little bit of detail about what that means. There's all different kinds of materials, plastics, metals, sand, glass, concrete. I've seen houses built 3D printed out of concrete. Ceramics, even food. You can 3D print different types of food. Now the food I'm showing in that picture there does not look overly appealing, but it's just a process, and it's something that can be done. Anything that can be liquefied or made into extruded, different things like that can be made into a additive manufacturing product. Applications, what are you using it for? You can use it for so many different things. And this list just keeps growing. Originally, it was just for rapid prototypes of the parts, but now they've realized, you can make the molds out of it. You can make medical things, surgical, medical and surgical are really growing because everything's custom. It's custom to, because everyone's anatomy is slightly different. You can use it specifically for the anatomy of the person that you're making the part for. So let me go through the list of the different processes and the advantages and kind of disadvantages of why you would use those. The first one we call photopolymerization, which is a mouthful. Imagine a tub or a vat, maybe let's say a foot by a foot by a foot deep. It's a container. And in that container, there is a plate or a table. And that table is on a cylinder that can move up and down within that vat. Now you fill that whole vat up with a liquid. It is a resin or a liquid that's kind of a liquefied plastic. You take that plate, that table, and you move it down very slightly. What it's saying there is the was that 98 10,000ths of an inch or whatever. So it's very, you can move it down a very slight amount. Then you take a laser or some kind of a specific light frequency and you shine it on that surface. So if you think of a part, look at the parts on the left, divide that up into, instead of looking at it as a whole, look at it as layers from the bottom up and just divide it into 10,000 layers. So each layer is shined with that laser. The computers just find that level or that layer, shine the laser onto that liquid. Wherever that laser hits, that liquid will solidify. Then the table moves down, just indexes down that same amount, and it does it again and again and again. So anywhere the laser hits becomes a solid, the rest of the liquid just stays liquid. So as it moves down, you can see the liquid stays on top, and it's in a big pool, and eventually that table will move all the way down to the bottom, and you'll have a part created by multiple layers. You can see some of the limitations of this, the size of the vat, the material, you're limited on the materials that you can get. This is what's also known as SLA. Some people look at something, it's called laser, I'm not really sure, SLA, it's stereolithography is what another name that it's called. It's highly accurate. It's great for small parts. It's harder for larger parts. Usually for larger parts, they'll do it in multiple parts and glue them together. One of the big applications is Invisalign braces. That's one of the way that it's made. What they'll do is they'll scan your teeth with a sensor, figure out exactly where all of your teeth are, scan each one of your teeth in relation to the other. Then a dentist using a computer program or an orthodontist using a computer program figures, okay, this is where your teeth are now. This is where I want them to be. And then they use stereolithography to create a positive of your teeth, essentially recreate your teeth from their existing condition to the desired condition. And then they do a thermoform of plastic over each one of those molds, those positives that they made, and those become the Invisalign braces. Next one is powder bed fusion. This is also known as SLS, which is laser sintering. So it's pretty much the same process I just spoke about with the liquid, but this one is different in that you're using a powder. So it's the same concept, though there's a tub or a vat with a table on top of it, but instead of being liquid in the table, a wiper comes across and lays a thin surface of a powder. Then the laser shines, and anywhere that laser hits, it pretty much just melts that plastic or that metal together. So it kind of fuses it all together, and then the whole table drops down, indexes down, it wipes another layer of powder over it, and this repeats. This sometimes requires some post production work. This isn't as, the surface is a little rougher, so it might need to be sanded a little bit. If you're just doing one of, it's kind of a more expensive process. You do have a lot of powder that you're dealing with there, but there are some distinct huge advantages for this. For example, look at the lattice work I'm showing there on the left. That is used, that's going to be there's a heat exchanger picture on the right, but there's a lattice there that they've made. Now, you can't, it's almost impossible to make that kind of a material, that kind of a shape, any way in the world except through this process. You can't really make it with the liquid because when you make a lattice like that, it's nice to have the powder will be in there, and the powder will be supporting that lattice, and it will keep it from collapsing. There's no way to machine that, because imagine if that lattice you're looking at is actually an inch thick. So how are you going to get inside and machine all those little bitty pieces? You can't injection mold it. So there's no way to make that except with some kind of a powder bed fusion type process, an SLS process. Where is this used a lot? Well, it's used in medical applications. What you're looking at here are variations of a hip replacement or a shoulder replacement. So typically what is done historically is that like a new socket is glued into a person's body. You know, the bone is removed, a new socket is glued in. Usually they're using some kind of an adhesive or an epoxy or something, and they glue it in there. At least that's what I've been told. But this process, now if you look at this, they've made this out of stainless steel powder, and they're doing the same thing. Instead of using a plastic powder, they're using a stainless steel powder, hitting it with a laser and creating this matrix, this lattice work that you can see in the pictures. The beauty of this is they will glue it partially or screw it. That's what the holes are for. They'll screw it into the bone in the person's body, but the bone will naturally grow into those voids in the steel, the stainless steel. So it will literally become part of the body, and it's definitely a much stronger than just a line of glue or adhesives, or even the screws themselves. They minimize the number of screws that they have to put in. So this is a new way that they're using this for different medical applications. Binder jetting. So this is very similar to the powder fusion that I just spoke about. But instead of hitting the powder with a laser to melt it together, they're actually hitting it with a glue or an adhesive or a bonding agent of some kind. So think of almost like an inkjet printer that's over the powder. So you put the powder down, then an inkjet printer prints onto it, but instead of printing ink, it's printing glue, super glue, some kind of a different type of bonding agent. There's all different kinds. You can see in the picture there that they're getting the whole rainbow effect that just gradually goes from one color to the next. And the way they're able to do that is because they just add some dyes, some colors into the glue itself. So it allows them to do a lot of different things when they're making the part. You can also see that they even have integral to the part the name of the company that's making it. So you can have integral things because it is kind of like an inkjet printer. These typically require some post-manufacturing, they can be, they usually, they'll have to go into an oven sometimes to kind of set everything. They're sometimes they're fired in a furnace, things like that. But it's great for integral colors. They can do a lot of different things with it, and it's slightly different than the SLA, no, SLS, but it's kind of the same thought process. All right, so kind of leading on to that, this was the next iteration. This one is really really becoming big. I'm seeing a lot of companies use this. It's 3D printing, and this is where 3D printing really comes into play, in that it is an inkjet printer, or very similar to the process of an inkjet printer, but it's jetting the adhesive material. So it will deposit little drops of the material layer by layer. So it's kind of the same concept with a surface that you're printing on, and that surface will just keep, either the surface will keep dropping down, or the ink gun, if you will, moves up. So it either move up, or it will move down. Sometimes there will be a additional curing lights. Maybe it's a UV color, a UV light that has to shine on it, and it will harden that plastic. One of the challenges with this is that you do have to have some support underneath it as it's being made. So sometimes if you had a part that was like maybe a T-shaped, you might need to put some supports underneath it so that it wouldn't, it wouldn't kind of fall down until you had a chance to get everything cured. But it's great for smaller parts. It's great for custom parts. It's fairly quick. You can have integral lettering, words into it. Some things that they're doing with it are, you can, like they're doing with the dental with the Invisalign, you can scan somebody's ear, and so you could have an earphone that is specifically designed for your ear. They're using this, not necessarily, they're showing earphones here, but it's great for hearing aids. Hearing aids are being done that way. In the past, where it's always been done with pretty much making a mold of someone's ear to make a hearing aid. So if you're going to make a hearing aid for someone, you would make a mold of the ear, and then you would make everything from that. Now they can pretty much 3D print a hearing aid around the electronics that that are needed for the hearing aid. So it's a little bit, it's a step up on that process. Sheet lamination. Imagine a sheet of paper, a ream of paper that you have in your, at your office. But this is, each layer is cut specifically to a shape. So it's essentially the same thing that we've been talking about, but instead of a process of heating things up or a laser or a light, instead they're using paper or some kind of other laminated material, metal, if you will. You can see the lower one there is metal. You can have integral to it. You can have maybe a electronics or a flow path for a liquid. So there's a lot of things you could do with it. It's a very cost-effective option. It's somewhat brittle. It's kind of not as precise as you would get with some of these other processes because it is just a sheet of paper. So, it's only as good as this machine can cut these layers of paper or as layers of aluminum foil, if you will. But it's great for a quick conceptual idea, a little thought process, something like that. Material extrusion. Now, this is the one that's very common right now. You can see these. I've seen these at Sam's Club. You can buy a 3D printer that it reminds me of back in the day when I was young, a Play-Doh extruder where you would put Play-Doh in and you'd squeeze it down and you would get different designs to come out. This is very similar to that in that you have a string. It looks almost like fishing line, a spool of this material that's fed into a heated nozzle or an orifice, and it just kind of goes around and prints a layer, and then it moves up and then it prints the next layer. There's a lot of different materials coming out with this. The accuracy is not that great. You can always tell these parts when you look at them because they are kind of surface level. You can really see the different layers because it's kind of a stepped finish. So it requires a lot of post-process work to make it nice and smooth, a lot of sanding, and it is kind of weak in the Z dimension, so it will crack in half. But it's great for functional testing. You can use it for see how something feels in your hand. They're using it. They actually use this. They have one of these in the International Space Station to use it to make parts. So it's a very common thing to use. There are some metals coming out now. There's challenges, but they're overcoming them pretty quickly. Another process, direct energy deposition. This is the last one we're going to talk about today, but this reminds me almost of a welding process. But instead of having a welding rod that you're welding on, you're using actually powder. You can't even use a wire feed itself, but you're using a laser to melt things. So it's an additive process. Using a laser, it's very strong. It's not very precise. It's not very accurate. It's only used on certain materials, but it's great for things like repairing parts, strengthening parts, maybe hardening an edge or a surface. So that's one of the big things with we've kind of grouped that in with additive manufacturing. This has been around in one form or another for a while, but we're adding it to additive manufacturing. So in the past, additive manufacturing has just been used for rapid prototypes. That's been the thought, but now we're looking more of how we use it in production. So it's got a reduced time and cost and improved efficiency when you're comparing it to a lot of one-of things. If you're comparing it to molding, that's not necessarily, it's going to be slower and more expensive than injection molding. But making one-of parts is probably cheaper than machining a one-of part in a plastic. So if you're going to hog out a piece of plastic or a piece of metal and make it, it's probably cheaper. It depends, and I'll talk about the cost breakdown here in just a second. But these are the kind of things we're comparing it to, molding and machining. So why switch? Because you're doing molding, you're doing machining now. Why should I switch to additive manufacturing? And I'm not saying that it's going to replace either one of those, but it's probably a different arrow in your quiver that you might need to have. So different uses of additive manufacturing, rapid prototyping. For example, jigs and fixtures. This is one of the fastest growing fields or uses of additive manufacturing. The picture on the right is a good example. Here's a vacuum cleaner part, very unusual shaped part. To hold it in place, looks like they're doing an inspection on the part there. To hold it in a very proper, the same orientation over and over again, you need a specific piece of tooling. Imagine that piece of tooling, that fixturing, that white piece there that's holding the part up, is going down the assembly line. And it's made of, maybe it's made of a couple pieces of metal or whatever, and it breaks. That can be an expensive thing to recreate. You might have to have machinists go in and machine that whole, it might be a complex setup for the machine shop, but if it's a rapid prototyped part, if it's a 3D printed part, you just set it in, you just request another one. They're used a lot for fixtures to hold parts during assembly. And it's very simple to do with additive manufacturing. If you've got the part already modeled in 3D, you just do essentially a negative of it, and you've got the fixture half designed already. The one on the left, here is a gripper to grip whatever that round piece of metal is. You can see you've got yellow pieces. You've got those little suction cups at the end. You've got a manifold at the top where you would create the vacuum. I can see 1, 2, 3, 4, 5, 6, 7, like 8 or 9 screws already on there. So there's probably a good, 30 screws holding this thing together at least. You could make that whole thing, except for the suction cups, out of additive manufacturing materials, and you might even be able to make the suction cups. You can make it all as one piece. Then anytime one breaks, you just make another one. So you eliminate the hoses, you eliminate all kinds of external parts that you would need just by doing it in additive manufacturing. Repair parts. This is big in the, it started off big with the antique cars. There would be, you know, parts on an old Ford or old Chrysler or something that you couldn't get these parts anymore. So they would do additive manufacturing to repair parts that were no longer made. So they could recreate it or repair it. This is, I think what we're showing here is a turbocharger from an aircraft, but you can see that they use some kind of a additive process and for the one on the right to repair the one on the left to make it where it is usable again using a stainless steel. So now they can get another couple years use out of the part. Casting parts. Casting is kind of new in additive manufacturing as far as I've known. It's only been a couple of years that I've seen this, but now if you're going to make a part out of a sand cast part, you can make the sand cast mold for pennies, if not, you know, $1 or $2. It's very, very inexpensive to make a sand cast mold. So they're using it a lot for making a printed core like what they're showing there, and then the finished cast on the right. Yes, it's going to be the tolerance and finish of a sand casting, so there is going to have to be secondary work for it. But you know, it drops the price tremendously. You can see the size of that, and the same part, you know, is less than $1,000, where it was $15,000 to do it traditional methods. So huge savings there. Prototyping. This is where I originally was exposed to this process, to additive manufacturing, and this is one of the areas that it's still used. I still use it regularly. I do product design and development for Missouri Enterprise. So probably in the last 2 years, I've had 10 clients that we've had to make rapid prototype or prototype parts using additive manufacturing. So we'll make a part that, sure, it's going to cost a couple, maybe $200, $50 to $100, who knows, but you can put it in your hand. You can feel what it feels like. You can see if the angles are right, if the grip feels right, if it fits with the other parts that you're going to work with. You can use materials that are very close to the finished part. So you can see, okay, this is how it would fit together. Now, you might not get, you know, if it snaps together, you may only get 1 or 2 snaps. You're not going to get it, you know, repeated over 100 times, but you'll get the idea of, does this fit? Do the parts fit together? So it really gives you a good head start on how this would look, how it would feel, you know, how it works with other parts. So when we talk about price is a big challenge with additive manufacturing. Now the prices are coming down, and the number of materials available are going up all the time. But let's look at this. This is SLM. We're talking selective laser melting or selective laser sintering, those type of things. But on the picture on the left, we're talking a machined part. So let's say you're machining a part in your machine shop, or you're having it done for a product that you're making. If it's done, when they say Bureau 1 or Bureau 2, they're talking about, you know, that just means machine shop 1 or machine shop 2 or injection molder 1 or 2. You can see that the cost for having that part machined If you're going to, you know, depending on how complex it is. When they talk about complexity, they're talking about number of features or different cuts or setups. So you can see at the top, we're saying, okay, the first one, there's 23 different cuts or setups, and it's probably different cuts or surface finishes, things like that. So the more complex you get, the further it goes to the right. So, you know, the one on the far right is a very complex part. And if you look at if you're using a CNC machine, I'm making the part out of stainless steel, the more complex it is, the price just keeps shooting up. But the more complex it is, the price on the selective laser melting goes down. It doesn't seem to make sense. Well, it does, because mainly what you're paying for is the material. You're not paying for the process. The process is the same for all of those. But the first one, you're using a lot more material than you are on the one on the far right. And if you look at where it stops, when it gets to a certain point, they can no longer make this using using a CNC process. It cannot be made. Maybe there are severe undercuts. Maybe there are internal chambers that you just cannot make. You don't have a drill bit that does that goes back and forth and makes a zigzag inside. You don't have a zigzag drill bit where you can do that with a selective laser melting. It's very simple to do that. You can have as complex of an interior in that as you want. So you can see that there's when complexity starts getting involved, there's a break-even point. It's going to be different for every different part being made, but there's a point where they cross each other, where it's actually cheaper to use an additive manufacturing process. On the right, we're looking at quantities. So injection molding, if you're only going to make 100 parts, the overall cost of that is going to be significantly higher than if you were doing it with an additive manufacturing process. And that's mainly because you have the cost of the tooling, you have the cost of setups, run some test parts, making sure everything comes out right. So it's not until you get into the few hundred parts, 500 parts, before the price comes down on injection molding. So if you're doing a short run, or let's say you have something that you only make 20 a year of, 30 a year of, 100 a year of, it might make sense to look at additive manufacturing compared to injection molding the part. Because if you're going to do injection molding, what's going to end up happening is you're going to end up, your purchasing department's going to say, well, let's just buy 2,000 of these. Well, if you're buying 2,000 and you're only using 500 a year, you have a 4-year supply. And what if your design changes in year 2? Then you're going to throw away half of those that you just made, and then you got to make a new mold. Or if you're doing it with additive manufacturing, it doesn't matter that you're only, 1 year's bad and you only sell 50, and the next year you sell 200, you're still ahead of the game. It's a great way to look at. A lot of companies we're talking to, we work with, have additive manufacturing machines, have design jet, where they're actually jetting the parts out. They're using the filaments. So there's a lot of different processes that are being used. And, as Amy said, the companies that we deal with, some of them even have excess capacity. So they'd be more than happy to work with you if you have a part that you need produced. So you're going to get a part produced. What does that mean? You've never used additive manufacturing before. Well, the first thing that probably has to happen is you need a CAD-based 3D model of what you're going to make. That's usually the biggest challenge. A lot of companies now, smaller companies, don't necessarily have everything on CAD. That's not a huge challenge anymore, because CAD is some kind of a 3D CAD system. So if you're just dealing with 2D AutoCAD, it might not work. You're going to need it made a 3D model so you can see all the different sides and all the different parts. From there, you create an STL model, which is a generic file. Then the 3D printing company or your software, if you have your own 3D printing equipment, you slice it into layers. Then it's produced. And sometimes there is some secondary finishing required, whether it's sanding, sometimes it's a little fill. Surprisingly enough, they use a lot of super glue to fill in, smooth things out. So you can get a very smooth finish. You can get painted. You can get different types of different sandblast finish, different types of finishes. But so those are the steps. So usually the biggest challenge is step number one, making sure that something is in CAD. So let's say you have it done and it is done in CAD. So what do you do next? Well, you go to an online pricing or quoting system. This is one for, I don't even know what object is the one on the top. I think the bottom one is for, I don't know who, I just pulled a couple of screenshots off of people that I was getting quotes for so what you would do is they pretty much quote you based on the volume of material that you're going to be making it with. What is your displaced volume, if you will. That's how it's pretty priced. They don't really even look at the complexity. Now they might look at the detail, how fine of a, maybe you have letters, imprinted into it, and you need, so it's maybe it's a quarter of a millimeter deep or something. So they might say, well, the resolution isn't there that you need. So as you can see on the lower one, there's a part being made, you can say the technology you want, the resolution, so you can get a higher resolution. Higher resolution makes the price go up. If there's a finish, sometimes it's a hand finish with sandpaper. Sometimes there's no finish and you'll finish it yourself. Sometimes you can get it polished up. You can get some parts made, and I have a client I work with regularly that gets parts made. They're doing some parts that are used in the plumbing industry. So they get parts made out of clear material so they can see what's going on internally, where the water is going, what happens, how it goes one way or to the other, so that you can get it clear. You can get the materials different colors, you can get different surface treatments, you can get it painted. So there's a lot of options you can do, and you just automatically get a price. And you can just, you upload the file to get that price, and then you just say go, and you just set up an account with them, and they'll send you a bill. It's very simple. The beauty of it is, so when you're designing for additive manufacturing, we talked about that CAD design a couple slides ago. One thing you have to look at is maybe you need to change your design. That's Missouri Enterprise. We do a lot of that. We're working with companies that have switching to an additive manufacturing process. And the beauty is that you can really minimize the number of parts. For example, this is an example shown on a company's website. Here's a part that was 16 parts plus glue to assemble this. It looks like some kind of a ductwork of some kind. You can take all of those parts, those 16 parts, those screws, those different clips, clamps, things, and you just make it out of one part. You have to do a little bit of redesign up front, but from then on, just think of all the labor you save, the assembly labor, the maintenance on it, the different part numbers you have to maintain, the screws, all that type of stuff is gone. You just have one part, and you can ship that part out by itself. There's no tooling whatsoever. So if you decide to change that internal divider and you want to move it over quarter inch to one side, you don't have to change the tooling. You just change the model. So it makes it a lot easier to do. It's lighter. It's used a lot That part is probably used in the aerospace industry because 3D printing is used significantly in aerospace. The one on the right, the picture on the right, that's another part that's kind of modified design for additive manufacturing. You can see that black stripe down the middle. The upper picture is what it originally looked like. That is what we would, in the industry, we'd call a living hinge. In the plastic industry, they call it a living hinge. So it flexes. It's kind of like what's on the lid of a shampoo bottle that you can, it's all one piece of plastic, but it flips over. So that's called a living hinge. Below, we're doing the same thing, but we're actually making it out of all one piece of equipment, but it changes material. And that black material down the center is actually a rubber type of material, where the white material on either side is a heavier plastic. And the lettering itself, that is built into the plastic itself. That's just a different color of that same white plastic. It's built in so that whoever has it can read where the part came from. Used a lot for weight reduction. Cars use it, or automotive manufacturers are using it to make brackets less lighter. You know, instead of taking taking multiple parts and clamping them all together, screwing them, welding them, tacking them together, they are able to make it all out of one part because they're using additive manufacturing. A beauty of it, a way that they do this is they do a strength analysis of it. So here's a part on the left that is a clamp, and then they did a strength analysis of it, and you can see from the picture in the middle, this is the only places where the strength, where the loads are flowing. Any place where it's not colored, there's almost zero loads. So they redesigned the part on the right. They take all that material out that they don't need because it does absolutely nothing but sit there and look pretty. So the part on the right is just where the loads go, and that way you've taken out all kinds of wasted material. Designed for additive manufacturing with using metals. On the left is a manifold. It's an air manifold for a hydraulic system. You can see all the different clamps that come off. They have to make sure that they're oriented in certain areas. You can imagine how tough that was to drill that. You're cross drilling, you're plugging the holes after you've cross drilled. Anybody that's had to deal with these kind of blocks, these manifolds, know what that means. On the right, everything is being done exactly the same, but it's all molded in one additive manufactured part with these internal grooves, everything already built in. So it's already completed. So you can change your design for that. Sand molds, as I spoke a little bit about, you can do things with sand. You can create that same part I just showed using a sand mold. So you kind of do a sand casting of it. So again, very inexpensive way to do this. So there has been a lot of changes in the software. So instead of using just CAD files, now in the CAD file themselves, they are getting to where you can change the color. You can change, you can see the pictures that below. Those are all done with additive manufacturing, and within the software, they're able to change, do a whole rainbow of colors, any kind of design, the artwork, and that's integral to the part. It doesn't have to be a secondary operation, doesn't have to be painted on, doesn't have to be silk screened. It's already built into the part, so you can save a lot of money in the production. So at this point, I'm going to hand it back to Miss Amy to close us out here.
All right, well, it's fascinating how many applications you can truly use this technology. Question, Bob, do you know if there's any restaurants out there that are currently serving 3D food items? Because if so, I mean, that's fantastic, but I'm just curious. Can I go to Starbucks? Am I going to get those little egg bites? Was that made by a 3D printer?
I've seen 3D printed food. It is not. It is exactly in the country that you would think it would be in. It's in Japan. Yep. They're doing 3D printed food in Japan. They're doing different types of noodles and things like that. So they're 3D printing designs they're 3D printing a happy birthday type thing out of noodles, or those type of things. So that's the only place where I've seen it done. I've seen extruded type food, but that's pretty generic. I mean, a Twizzler is an extruded piece of candy. Yes, but to get more complex, they're looking at 3D printing cake toppings and things like that. I have not seen anything where they're like 3D printing artificial eggs or anything like that yet.
You can't just 3D print some meatloaf for dinner yet.
Well, you probably could. I'll be right behind you tasting it. So.
Can you tell that I haven't eaten lunch yet? Okay, we do have a couple questions here I want to send your way. One is, does MEP have the ability to provide vendors access to 3D CAD systems?
3D
And that's from
CAD.
Rachel. Rachel is one of our A students.
Okay.
Hi, Rachel.
Yeah. 3D CAD systems. The MEP, we don't really have, the quick answer is no, but there are a lot of 3D CAD systems that are available fairly inexpensively, if not free, online. The problem with that is the robustness of them. You're going to be limited by the free versions that you can get online.
So they're the light versions, essentially.
Yeah, it's going to be the light versions. So you're going to lose a lot of the, filleting and maybe some, there's a lot of, you'll be able to make shapes, but some of the very fine details you might not, it'll take you a lot of extra effort to make some of the more complex shapes. The problem is that the financial model that they're working under, they're trying to make money by selling the software. So
sure, there's some limitations.
Yeah,
right?
Yeah. So unfortunately, no.
Okay. Before I go to the next question, I am going to go ahead and launch this before I know it's getting close to 2, and your tummy may be rumbling like mine, but I'm going to go ahead and launch that poll right now. Please, everyone that's still on, answer those questions. There's just a few questions here. Did you find this webinar to be helpful? A very easy question to ask, or to answer, excuse me. Do you plan to use 3D technology within your company in the near future? Have you explored other forms of technology to improve your business, such as digitization, going from manual processes to digitizing some of those processes and really being able to access that data and use it to make decisions in the future? Same thing as cobots and robots. And then we also have, how did you find out about this webinar? And that, again, just helps us. Looks like 100% of you found out by email. So yay, glad to hear that. Please continue to send in those poll questions or answer those. We have 7 of you that have completed it. So please, few seconds here. I'm going to leave it open for another minute. And as I do that, Bob, we have a question from Rob Rolfs. What's the biggest printer that's readily available for metal?
Oh, that's a good question. Because things are changing daily. The last I saw, there was one, trying to think of what company was it. It might have been, well, I can't remember the name of the company, and I'll dig that up. But it was a little over a foot by a foot. So it's not really big. We're talking a cubic foot is the biggest part, and it was a pretty massive machine too, because you're talking a major size laser that you have to use to center that metal. Man, I wish I could remember the name of the company.
Well, if you think of it, you can get back with Rob, or Rob.
Yeah, I will. Yeah.
Make sure that you reach back out to Bob Beckman at the end, and
there's a lot of them are
the
smaller sizes, and they have been doing the smaller sizes and kind of attaching pieces together after they're made. But I'll dig into it. They might be bigger than that now, because I haven't run into a need for that, so I haven't had to go into that for quite a while, for probably a year now.
Okay. Well, if there's any additional resources too, we can certainly share those with folks
Yeah.
or follow up with Bob. He again is our tech champion for Missouri Enterprise. So if you're wanting to look into any other technologies, I believe there's 9 really kind of the focus areas for the MEP system nationwide, ones that our centers are looking towards to implement or help manufacturers implement more into their processes. So just feel free to get in touch with Bob. He'll share all kinds of interesting information about technology. And yes, Rachel, she also looks forward to the 3D printed meatloaf. So whenever that does become available, Bob, I hope you let at least the 2 of us know.
Sure.
That sounds really good.
Well,
thank you so much. It looks like 67% of you plan to use 3D printing technology within your company in the future. So that's very exciting. I'm glad that you found this helpful. And I know there's a lot of information that we packed into here. So thankfully for you, you will receive this presentation so you can share it with other folks within your company, and hopefully it'll be more thought-provoking and you can move forward if you choose to. So thank you, Bob, so much again. As always, really appreciate it.
Do you give them my contact information?
I will make sure that is in the email.
Yeah. If you got any follow-up questions, I flew through this pretty quick because I had a lot to try to cover. So please shoot me any other questions that might come up. I'll be glad to help.
Okay, great. Thank you everyone for joining us. Have a great rest of your week.
Thank you.